Okay, so here comes a couple of examples to iron out this section, really what you're required to do. Nothing super major. There's nothing really new, but here is kind of a process that you can follow for the homework in section 8, okay? So first, when they ask for the interval of convergence, always, 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 this is the way to go, it seems, in the homework. You take the ratio test, and when you get your limit finally, and it's going to involve a variable x, you're going to set it less than 1 to force convergence. But, here's what could happen. You ready? Here's the other cases that could happen. One, you take your limit and you get 0. By the way, 0 is always less than 1, so no matter what x you would have plugged in, you get it would still converge because here's x multiplying with something that shrinks to 0. So in that case, no matter what x you put in there, it converges. So your interval of convergence is really the whole real number line. That can happen. What could also happen is you take your limit and you get the reverse, the opposite, which is infinity. No matter what x is, the thing still marches off to infinity. So the only thing it might converge for is that center number I talked about in the first video, which is wherever they center it, there is a number that when you plug in, all the terms turn to 0 except the first number, okay? Those two, okay, can happen. It can happen. So it doesn't converge except for one number. And the third one that we ran into in the previous video was you do get a finite interval of sorts. For instance, we got absolute x, and then we forced it less than 1, and we came up with an interval. Okay, those are the three possibilities, and that's actually a theorem. And it said it converges at only a, it converges with a at the center, and you've got some sort of interval around it, whatever it might be. And the third option is, yeah, it converges at a, but it converges everywhere. Okay, so it's all real numbers. This is like a single number only. That's the one that causes everybody to be 0. You get some sort of finite interval. It doesn't go forever anywhere. Or you can get all real numbers. That's what it'll converge for. Though that's a theorem. We don't prove it, but there's a theorem in this stuff. So let's talk about the method. Let's go for it. Let's do this particular problem from the homework. So what do? They want the interval of convergence. I whip out the old trusty ratio test, which says take the lim as n goes to infinity, absolute value. Remember, minus 1 melts away. So we're just going to go x to the 2 times n plus 1, remember, all over 2 times n plus 1, right? Factorial. That's the n plus first term. So I just replace n's with n plus 1s. You got to be careful with the algebra, for sure. And then we have 2n factorial, and downstairs we have x to the 2n power. Now, this is going to be tricky for a number of people to cancel stuff, but we just have to plug away with this thing, okay? In fact, I'll rewrite this a little bit better. I'll say it's equal to, this helps me out too. I think what I would normally do is I really have x to the 2n plus 2 power, and downstairs I've got 2n plus 2 factorial, and then we have 2n factorial, and then downstairs we have x to the 2n. Okay, so hopefully after the previous homework exercises, we can kind of cancel it. But I'm going to help people out. I'm going to rewrite it over here because I have a feeling I'm just inspired to do this. We've got absolute value. I've got x times x. Well, let me write it this way. I've got x to the 2n times x squared. That's 2n plus 2. That's what it looks like, believe it or not. And I did that because down here I have x to the 2n, right? 2 more makes it x to the 2n plus 2. I know it's math, baby. Here I've got 2n factorial, but downstairs there are 2 more. So I could write this as 2n plus 2, 2n plus 1, and then 2n factorial all the rest of the way. Yeah, that's the mechanics of it. We cancel these guys, they're gone. We cancel the factorials, they're gone. And you can see we haven't taken a limit yet, but what we have is n going to infinity. And let's see, I'll write it as, like, you know how I do it. I write it to the side, or you're learning how I do it. And then I've got down here 2n plus 2, 2n plus 1. And I've set myself up kind of nicely to take the limit. In this case, the limit, what happens here? What does this guy do? As n goes to, yeah, it goes to 0. That's right. So we get a limit that says absolute x times 0 is 0. It's one of those cases that I just mentioned up here. It's the first case. We're getting 0. The question is, when is that less than 1? Always. What if I plug in a huge number for x, like 10 billion to the 10 billionth power? Times 0 is 0. No matter what number you plug in for x, it converges. So the interval of convergence is, let's write it out, the interval of convergence in this case is minus infinity to plus infinity. It just means any old value of x will work. There you go. You can pause that and stare at it. It helps with the homework, I hope. And I think I have one more example. Yep, this is the last example. I thought I was going to do another, but it would have been redundant if I did like the series for e to the x we talked about in the previous video. It's just like the other one. You can go back and check the series for what I called series for e to the x is really n is like 0 to infinity, x to the n over n factorial. You're going to find it's also minus infinity to infinity, so you can try it. Okay, it's real quick. Okay, so this last example for this video is this guy. Looks like a mess, right? It says find the interval of convergence. You know what I'm going to do, right? You know it, right? Ratio test. So will you. This whole section, that's how we do it. So lim, here's the mechanics though. Watch out, absolute value. What happens to the minus 1? Bye-bye. So I'm going to put x to x minus 1 upstairs, but to the n plus first power because it's the n plus first term. Downstairs I've got 2 times n plus 1 minus 1, and then times 2 to the n. Plus 1, I almost forgot. Now I'm going to turn this guy over and I'm going to write 2n minus 1 times 2 to the n, and downstairs here would be x minus 1 to the n, because we are inverting and multiplying. We're going a sub n plus 1 divided by a sub n is a sub n plus 1 times 1 over a sub n. We're flipping it over, and that's what we did there. Okay, time to cancel. Let's do the canceling now. Oh wait, let's write it a little better. So we have lim, n goes to infinity. We've got absolute x minus 1 to the n plus 1. The only thing I'm really going to do here is this guy right here. He's 2n plus 2 minus 1, so he really becomes 2n plus 1, and then times 2 to the n plus 1. And over here, 2n minus 1 times 2 to the n, and then downstairs is x minus 1 to the n. Okay? Now we get to cancel stuff. Let's see, yeah. Gone are the x's, and we're just left with one of those guys. But look at the powers of 2 also. Do you see that? This guy's gone, and he's all gone except for one of them. That's about all I got. So rewriting it, I get lim as n goes to infinity, absolute value. I'm going to tuck this x minus 1 off to the side and look at this new ratio. And what do we have? Oh, we have a 2. Let me put the 2 under him too. And what I have here is 2n minus 1 over 2n plus 1. You're watching a guy who's done this a lot. I always tend to tuck it over here to the side. Whatever is involved, anything that doesn't involve n, I move it, and then I go times, okay, what's happening with n? And I did it up here too, if you remember. I just put this x squared by his lonesome there, and then what's going on with n. So I separate it out. Because as n goes to infinity, and this is something maybe I should have said at the previous video, as n goes to infinity, I'll write it out, as n gets larger and larger, x stays the same. What do you mean? It's a variable. Well, it's a variable it's a catch-all, it's a holder for you to put any number you want. But once you put that number in, it's stuck. N grows and grows and grows, and that x is whatever it is. Okay? I'm not saying that's comprehensible just yet, but who's going to infinity here? You know who. just the ends. That's why I separate them out. I go, they're not moving, but the ends are. I can tell what this limit is. Look at that, 2n over 2n. You get 2 over 2, which is just 1. Okay, so this particular limit becomes absolute x minus 1 over 2 times 1. Or that's a big one. Or you can just simply say times 1. Or it's equal to absolute x minus 1 over 2. We found the limit. In this case, it's not 0, it's not infinity. Instead, we've got a solid thing here. And so for us to have convergence, we force it less than 1 for convergence. And look what it does to x. It restrains or restricts x. It's saying that absolute x over 2 is less than 1. Okay? So that means that bookending minus 1 less than x minus 1 over 2 less than 1 occurs. But now it's different. It's not just x. It's an expression with x. If we solve it, let's say we multiply both sides, everybody by 2, we get minus 2 less than x minus 1 less than 2. And then we're going to add 1. Just like we do in algebra 2 or something. We get a minus 1 less than x less than 3. And there's your interval. Okay, there's your interval. All right. You remember how it said x minus 1? So here's a number line. Here's minus 1. Here's 3. If you go back to the series and you look at it, you go, hey, what if I plugged in x is equal to 1? If x equals 1, you got nothing but zeros except for the first number, whatever that is. In between these two guys is the number 1, and that's the center, if you will. The radius, they'll talk about a radius of convergence too. I don't really care about that. It's how far out from the center the series actually converges. But there's your interval so far. You know what we have to do? We have to test the endpoints, and then we'll be done. Okay, so that means we need the series, which is way up here. Where are you, series? It's got the minus 1 in it. Don't forget that. A lot of stuff, a lot of moving parts here. So the series is n is 1, I think, to infinity, minus 1 to the n. I've got, gosh, I've already forgotten. It's, there it is. Let's see, 2n minus 1, 2 to the n. So we have 2n minus 1, 2 to the n. All right. And then we have this x minus 1 to the n. I think that's all correct now. You got to get it right. Looking pretty good. Okay, good. But now what we're going to do is going to be weird, is we're going to plug in the endpoints to see what happens. So I'm going to erase that guy. I'm going to say, let's say we're testing x is equal to minus 1. So we plug in minus 1 and we get this. Okay, so what's going on here? Let's see. I've got its series minus 1 to the n, and we've got 2n minus 1 times 2 to the n. And then what we have here is minus 2 to the n. Look at all that stuff that's going on. Look at it, all of it. So I've got like minus 1 to the n, minus 2 to the n, over 2 to the n, and forget the other guy. What all happens here? Well, everything to the n would say minus 1 times minus 2 over 2. That's 2 over 2, which is 1 to the n, which is just 1. So our series devolves when you plug that number in. All these guys just turn into 1, so we're looking at 1 over 2n minus 1. Now I'm going to cut to the chase here because this is a lengthy guide, but your work, maybe I shouldn't. Your work would look something like this, so if you bear with me, you'll see everything you have to do. So what about this series at x is equal to negative 1? My intuition says it's like series 1 over n, which is a divergent p-series. Really? Okay, let's go with that. No. So I'm going to use the limit comparison test, and I'll write lim as n goes to infinity. This is an old problem for you guys. 1 over 2n minus 1 divided by 1 over n, or invert and multiply, and we get a lim as n goes to infinity of n over 2n minus 1, which is 1/2. Limit comparison test for a tiny endpoint, but it's important to show it's not 0 and it's not infinite, so they both do the same thing. So series 1 over 2n minus 1 also diverges. So in your number line here of convergence, that's an open circle. Okay, so you don't put any line under. -1 doesn't work. Got one more. What about x is equal to 3? Here comes the series, -1 to the n. Downstairs is 2n minus 1 times 2 to the n. And this time, instead of -1 to the n, we're plugging in a 3. Okay? If we do that, look what happens to those powers of n, the n powers. You've got series -1 to the n. We've got downstairs is 2n minus 1, and then 2 to the n, and then another 2 to the n, huh? You see that? We can actually cancel those guys. Goodbye, goodbye. Yeah, this is the tedious part. You think you're done, but you still have the little endpoints to mess with. It's worth a couple points. -1 to the n now over 2 to the n minus 1. That typically happens. Either you get an alternating series or you don't have an alternating series. In the first endpoint, no alternating, but in this case it does alternate. So guess what? I have to do the alternating series test on it. So 1 lim, as n goes to infinity, 1 over 2, are you kidding? All of this? Yes, is equal to 0. Check. 2, write down the n plus the nth term, which is 1 over 2n minus 1. It's going to be bigger than 1 over 2 n plus 1 minus 1, which is the n plus first term. So it is decreasing, check, and so therefore it converges. So up here, 3 causes convergence, -1 divergence. You have a little line there. But finally, after all that work, you can say, therefore, the interval of convergence is -1 to 3, include 3, don't include the -1, and we're happy. A little bit of tear or a sweat or whatever it is. You know, it's a lot of work. You got to test the endpoints. That took half the battle right there. But it's good stuff. We found all the numbers for which that series converges. I hope this helps you guys out with the homework. There's a lot of little details here, but it's the same thing kind of over and over again. Good luck.